Okay, hi everybody. Thank you for coming. This has been a great conference so far. I think this is the second YMC I've been to. I think I came maybe like 10 years ago. My wife is from Columbus, so I'm often in town for family reasons. Anyway, thank you guys so much for coming. So yeah, I'm gonna talk about a math problem that I like a lot and have liked for a long time. And then I'm going to talk about sort of like what happened when we tried to bring some of these new technologies of machine learning into contact with these math problems. I mean, as you guys probably know, there's like a huge amount of interest in machine learning in the world. And in the theory of machine learning, there's been a huge amount of mathematics and buy-in from mathematicians to think about what is the underlying theory of machine learning? Why does it work? Under what circumstances does it work? So that's kind of a math for machine learning arrow. Machine learning for math is like a little bit newer, and that's something that's developing quickly right now in a lot of different directions, just one of which I'll talk about today. But in order to start, I mean, well, of course, I want to talk about this, this question that has aroused so much interest over the years. So let me sort of set it up. So question, how large can a subset S of, and so this is a question about subsets of vector spaces, but this is a sort of combinatorics question. We like finite sets, so I want this to be a vector space over a finite field. So let's say Z mod 3Z to the n B. Okay, if I don't say any more, then we know the answer, right? 3 to the n, because that's the size, that's how many vectors there are in this finite group. But of course, there's a condition. This is an extreme combinatorics question. If there are no 3 distinct x, y, and z in S, such that the 3 vectors sum to 0. So there's sort of a set of sort of forbidden triads. You never want to have 3 vectors which sum to 0. So there's lots of questions arise here immediately. But one thing I want to observe is that this question has many, many equivalent formulations. So I've given you one, and let me say a couple of others. So equivalently, well, I could write x plus z equals negative y. That's a sort of, why did I even bother to do that? That's like very visibly equivalent. Well, remember, we're working mod 3, so negative 1 is equal to 2. So that's equivalent. Or maybe I'll even write it like this. I'll just divide out the 2 by both sides. And now that looks kind of familiar, right? I'm saying another way to say this is I never want one vector to be the midpoint of the other 2. Or another way to say it is I never want x, y, and z to be an arithmetic progression. So the definition of an arithmetic progression in any abelian group is the same thing as the definition of an arithmetic progression of integers that you surely already know, which is that the middle number is the midpoint of the 2 outer numbers. So we would say, so no 3-term arithmetic progressions. And I write this formulation to sort of give some hint as to why people started thinking about this question in the first place, which has turned out to have lots of interest in its own right. But the question of how big can a subset of the integers be with no 3-term arithmetic progressions is a very long-standing question in analytic number theory. The first good results in this problem were made by Roth, I think in the 1930s. So this was, I think, originally thought about as a model for questions about large subsets of a sequence of integers 1 through n with no 3-term AP. But even a third way to say it is I mean, it's worth thinking about, what does a line in this vector space look like? Okay, so if I mean, one way to define a line is I give you 2 points and say, like, look at the line through it. So note, let's see, I want to say one more equivalently over here, but I need to make a note over here to sort of, before I write, sorry for being a little bit nonlinear. So a line in Z mod 3 to the n consists of, all right, so maybe I have 2 points, x and then y, which should not be equal to x. And then you could sort of say, well, a line is going to have all kinds of things, right? It's going to have like every linear combination of x and y. And then you sort of start to write them down. You're like, well, I guess there's like, we have to be a little careful because it's a linear combination of x and y where the coefficients sum to 1. Right? You guys know the formula for, and like, so I guess it's tx plus 1 minus ty. But what can t be? It's either 0, 1, or 2. There aren't so many numbers in Z mod 3z. So actually in this space, a line only has 3 points. And t equals 0, that gives you y. T equals 1, that gives you x. So the only other point left is t equals 2. But then t and 1 minus t are both -1, and you get a thing like this. So literally, in the lines over Z mod 3z have this very funny property that each point there's only 3 points on the line, and each point is the midpoint of the other 2. So equivalently is to say that no 3 distinct points are collinear. So having written these 3 equivalent formulations, and they all seem like natural questions. Okay, I might want to look for sets where no 3 sum to 0. I want to look for sets where there's no 3-term arithmetic progressions. I might want to look for sets where no 3 are collinear. And over Z mod 3z, all of these questions are the same question. So I'm sort of implicitly answering a question you didn't ask, which is why 3? Why? I mean, I could have taken any vector space over any finite field. And the reason is simply that over larger finite fields, these questions are still active, but they just all become different. And so somehow when we want to sort of study this type of question, this is the most natural setting in which everything coincides and there's like one natural question to ask. So actually it's a sort of fun exercise if you get like bored with something else I say, or you like hate computers and you don't want to hear about machine learning or like whatever. As an exercise, if I did this over Z mod PZ to the n, if I did a mod 5 or mod 7 or something like that, 2 of these questions would still be interesting and 1 would not be so interesting. So I'll leave it as an exercise to figure out which is the less interesting one. When 3 is not 3 and 3 is something else. Okay, and I guess I should say, all right, what's my board protocol? Do I just not use those and use these lower ones? What are people doing?
On your right, there.
Oh, no, I can't be bothered. Okay. So and maybe I'll comment, I think because I want to talk about computers today, I'm not going to sort of tell this whole story, but I'll sort of say equivalently, the special case n equals 4 of historical interest because you may know, if you've played the card game Set, which is how I first learned about this question, that game is a deck with 81 cards. The 81 cards are naturally in bijection with the 4-dimensional space over Z mod 3z. And although it doesn't say this on the box, the rule of the game is that you take 3 cards whenever the 3 cards are collinear or whenever they satisfy any of these equivalent conditions. So equivalently, when n equals 4, what is the largest, or I guess to be more precise, just to say how big is the largest collection of set cards with no legal play. So I think like a lot of people, this is actually how I first encountered this question. More precisely, I mean, this is many years ago now, but I was playing this game against Ingrid Dobish's 8-year-old son, and he was completely crushing me, and it was really embarrassing. And I was like, what can I do that an 8-year-old can't do? I got to prove a theorem about this game. Even though I can't win the game, at least maybe I can prove something. So if you have never thought about this problem before, whether in the set context or in the sort of combinatorial number theory context, I think the best way to get a feeling for what this problem is like is just to do an example. So n equals 1 is a little bit too easy, so let's do n equals 2. So here I'm going to draw it. So here's my picture of a two-dimensional vector space over F3. I guess I have 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. So in the set context, this would be like taking your set deck and taking out only the cards that are like red and have a squiggle, and then there would be like 9 cards like that, and you could lay them out in nothing like this. And the question is, how many of these guys can I have and still have the property that no 3 of them sum to 0, or equivalently no 3 of them are on a line? So let's actually take here, and I'll time it. Let's take sort of 3 minutes and try to make like the biggest one that you can. And if you want, maybe because we have a nice big room with a lot of people, maybe if you could like turn to the person next to you and discuss this, and then we'll reconvene in 3 minutes and sort of see what we got. Because otherwise, it's impossible to have a feel for this problem unless you sort of try to actually do it. Okay, our timer is up. Gosh, I hate to stop it when there's so much activity, but we could just like all sit here working on this problem. But let me hear how far we got. How big of a set did we find? You can hold up your fingers. I want to see what people got. Okay, I think. Okay, I see a lot of 4. 4 is indeed correct. Like usually I have like somebody with like a 6 or a 5 that I can like shoot down. I guess maybe I let you guys work too long. Yeah, so what I hope you guys saw as you worked on this is that there are lots of lines that look like lines, right? Like these guys sum to 0. They're not allowed to be all in there. So do these guys. But then the thing to be careful of is that there's also like 0, 1, 1, 2, and 2, 0 also sum to 0. So sort of to date myself, I call these like, the asteroids lines, when your little spaceship like flies off the edge of the screen and like sort of comes back here. So yeah, any of these sets of 3 things, both the ones that look like lines and the ones that look like kind of broken lines, all are excluded. And it's not so hard. It's not so hard to find 4 that have no line. It's a little trickier, but you can sort of do it basically exhaustively to show that you can't do better than 4. So what 4 did people get? Because there's a lot of choices. Somebody tell me. How about you? You in the red shirt. So that's very. 0, 1, 1, 0, 1, 2, 2. Okay. Dot. Okay. I like that. But I'm not going to draw it because there's like a nicer one I like to draw. Way in the back. Oh yeah, okay, great. So we could do like the outer corners of the square. Yeah, let's do that. Okay, so I'll circle these guys. And what I want you to note is that we've actually only used 2 of the possible digits. It's kind of like a discrete Cantor set for the real analysis fans. And there's a reason that works. The reason is that if I only use 2 of the digits, look at what happens. Like I try to find 3 of them that sum to 0. And even let's just look at the first digit. These are all 0s and 2s. And so if I have 2 2s and a 0, that doesn't sum to 0. And if I have a 2 and 2 zeros, that doesn't sum to 0. So for these guys to sum to 0, the first 3 coordinates all have to be, the first coordinates have to be either all 0s or all 2s. But then that's also the same for the second coordinate. So I mean, for these guys to sum to 0, the first coordinates will have to be the same, and the second coordinates will have to be the same. And that means that the 3 vectors would all be the same, but that's not allowed. So I mean, this is why it's very important that when I originally formulated the problem, I said distinct, because if I have 3 is 0, right? So if I had x equals y equals z, certainly x plus x plus x equals 0. So that's not a violation. So yes, a setup like this, if I only use 2 of the possible digits, then I always get a set with no 3-term arithmetic regression. So what I like about this, because it's going to be kind of the theme of today, is that it's an example, but it's an example that if you sort of think about why it works, it gives you an idea for a general piece of information about the problem. I mean, this is an example just in 2 dimensions, but so what this tells you is that for any n, I guess I would call it 0, 2 to the n, has size 2 to the n, and has no x plus y plus z equals 0. Okay, so let's introduce a little bit of notation. Let's just say oh, so by the way, one thing you might ask, if you were going to try to sort of think about this problem, you might say, well, what if I just, and this is a very productive strategy in many parts of combinatorics of this kind, you might say, well, what if I just started putting down vectors at random? And every time I chose one which violated the rule, I was like, okay, don't add that one, exclude that, draw from your Scrabble tiles again and like put down a different one, and keep on doing that until you like run out of space. And it's actually, again, I won't sort of work this out on the board, but if you try to do that and say like, how big of a set would I get? It's way smaller than 2 to the n. So that's already a sign that something interesting is going on with this problem, that sort of any kind of random selection method, and you might naturally think, oh, maybe that's as good as you can do, but 2 to the n is like much bigger than in some sense by rights you should expect. Like if you were to put down, another way to put it is if you were to put down 2 to the n random vectors, or now I should have like worked this out of my notes, but I think if you put down any number of vectors bigger than like root 3 to the n, the chances are extremely close to 1 that there's a violation. You would have to get extremely lucky in order to find a set with no x plus y plus z equals 0, but I guess we just are lucky because such sets exist. And indeed, when I first encountered this problem at the hands of my drubbing by Ingrid Dobishy's 8-year-old son, I was like, oh, so let me prove that this is the biggest, because it's sort of crazy that there's one that's big. And I worked pretty hard on it for a week or so, and I couldn't do it, and I couldn't do it, and I started to feel even more dejected than I had when I was getting crushed in this game by an 8-year-old. But then I found out that the reason I could not prove that is because it's not true, and then I felt much better. Right? Because it's bad if there's something that's true and you can't prove it because you're just not clever enough. But somehow if the thing is false, then it's like very good that you couldn't prove it, right? So it's, so indeed, even in 3 dimensions, it's false. So I'll draw sort of a little schematic. Here's my picture of 3-dimensional space over the field of 3 elements with 27 boxes, and well, certainly, if this is to not have any solutions to x plus y plus z equals 0, that has to be true within each slice. So already I know that each slice can have at most 4 dots in it. And so maybe I'll even put the configuration that I already drew in the first slice. Now you could put the same configuration in the second slice, but then you would find that there was no room to put anything left in here, and you would actually be doing that again. You would have chosen, like if this was 0, and if this was third coordinate 0, and this is third coordinate 2, you would be doing the construction we already gave. But it turns out that if you do a different one here, that leaves you room for one more. And yeah, and maybe I can't resist saying, and I'm not going to sort of follow this direction in this talk, but since there are, I know, plenty of number theorists in the room, it turns out that one way of describing this set, I think I'm remembering the equation correctly, is that it's the solutions to z equals x squared plus y squared, right? Because I mean, if I think of it's a three-dimensional space, and I'm sort of like cutting out this equation. So this is the set of x, y, z, such that z equals x squared plus y squared. And then ready? World's worst proof that this has no 3 points on a line. Well, we know what x squared plus y squared equals z looks like. It kind of looks like a paraboloid. And like, look at it, a line can't hit that 3 times. Okay, that's a very bad proof because this is a picture of what this equation looks like over the real numbers, and we're not over the real numbers, we're over a field of 3 elements. But like, if you want to know what arithmetic geometry, my research area, is about, it's basically about like drawing pictures like this and pretending they're correct over a finite field, and then somehow proving that everything works. So I spent a lot of time sort of thinking that there was going to be kind of an algebraic geometry approach to this problem, and that like didn't work actually. So let me say a little bit about sort of the history of this problem sort of like since that time. So let's introduce a notation. Let's say f of n equals size of largest. Oh, and I forgot to introduce some notation. So let's denote by a cap set a set which satisfies the property that we want. It's a commonly used term. Cap set in z mod 3 to z to the n. And then we can make a little table. Okay, so when n equals 1, this problem is pretty easy because you just have a line, 3 points, and if you have all 3 of them, then you have a line, and if you don't, then you don't. So you can have 2 out of the 3. We already established that f of 2 equals 4. F of 3, we thought it might be 8, but then we saw that it was at least 9, and in fact, it's exactly 9. And now for the original problem of set, it turns out that the answer to this question is 20. And that was actually, that is sort of a folk theorem that sort of people have worked out who play the game like over the years. And by now it's exhaustively proved, so let me give you another couple of examples. And actually the reason I didn't leave myself more room on the board is that this is in fact the complete list of values of n for which we know the exact value of f of n. So that's it. And then you're like, well, that's a pretty puny list. So now let me sort of say the first words about computation I'll say. Why do we have such a puny list? Like, why don't we just check? It's a finite problem. Well, think about what you would be asking yourself to do. I want to find the largest subset of z mod 3 z to the n that has some property. Well, how many subsets of z mod 3 z to the n are there? It's subsets of a set of size 3 to the n. So there's 2 to the 3 to the n subsets. Okay, that's a pretty bad number. It's too big when n is of any size at all. And indeed, I can tell you that I think the last one that you can actually do by looking at all the subsets is actually, I think it's this one. I think even for n equals 4, you have to sort of, you can do a lot of pruning first and get it down to something where you can do exhaustive search. And then these theorems really are theorems where you sort of have to sort of sit down and prove something, and there's sort of not so much of an element of exhaustive search in it because the space is already much too big. So this is definitely a sort of, it's a finite problem, but it's sort of a non-computationally finite problem if you want to get it done before whatever, the heat death of the universe. So I think for a long time, so let me sort of say what was known about this problem. Okay, so we know that maybe I'll sort of put lower bounds over here and upper bounds over here. I already explained that f of n is at least 2 to the n because we explicitly constructed a subset. But actually it's a little bit better than that, because if I have, let's say, now that I have this, if I wanted to make a big cap set in 6-dimensional space, I could just make it by taking 2 copies of this set. I could say, like, look at all 6-dimensional vectors where the first 3 coordinates satisfy this and the second 3 coordinates also satisfy this, and then I would get 81. So actually, any 2 cap sets can be concatenated in this way, and that gives me the fact that f of m plus n is at least as big as f of m times f of n. So that means that any time you generate a big example, you have the potential to sort of improve your lower bound for all n. And in fact, like by methods like this, but a little bit more clever, there was a theorem of Adel from the early 2000s that got a lower bound of about, I think it was, I'm not going to remember the exact decimal, but I think it's about 2.208 to the n. For upper bounds, it was proved by Meshulam in 1995 that f of n was at most 2 over n times 3 to the n. So before that, it was not even known that the density of this set had to go down to 0. Like for all we knew, like maybe it could be that you could have like 1% of all vectors and you could like choose them so carefully that there would be no solution to x plus y plus z equals 0. But Meshulam showed that this was not the case and that the proportion of vectors you had was something that goes to 0. And then, after thinking about this problem on and off for a long time, there was like a really interesting combinatorial breakthrough of Kroot, Levin, Potch, followed up by work of myself and Dion Gijsweit, which showed that this was bounded above by 2.756 to the n. So I think the question had been, is there some exponent lower than 3 that gives an upper bound? And indeed, the answer is yes. So a couple of comments about that. And I'm not going to say, again, in a different kind of talk where I wasn't going to talk about computers, I would sort of say something about the proof of this theorem, which sort of took the problem in interesting directions based on this breakthrough of Kroot, Levin, Potch. I'm really not going to say that because I'm going to talk about lower bounds mostly today. But I'll just comment that one interesting thing that happened is that you might remember that this problem was originally devised as an analog to this question about subsets of the integers with no 3-term arithmetic progressions. So you might think, oh wow, this vastly improved upper bound should tell you that there's a strong upper bound on the size of a set of integers between 1 and n that have no 3-term arithmetic progressions. The only problem is that's not true. We actually know there's a classical construction of Baron that gives you actually very large subsets of the integers with no 3-term arithmetic progressions that are sort of closer to this size. So in fact, what happened when this was proved is that it kind of broke the analogy with the problem that it was originally supposed to be an analogy for, but by that time this was understood to be an interesting problem in its own right. But what I want to emphasize is that these two numbers are still really different. And you know, for a lot of questions in combinatorics, and certainly in number theory, somehow I think mathematicians, we may not be able to prove it, but we sort of have a very strong consensus about what's actually true and what we're trying to prove. And I think for this question, one thing that I think a lot of people find appealing about it is that there really is no consensus about what's true. Like if you ask people, okay, is the actual answer, is it closer to this or is it closer to this? I think there's no consensus. People don't really know how to form intuition about it. And I think indeed this theorem, it wasn't like this was a conjecture that everybody was trying to prove. It was like really a question. People were like not sure whether to think that a bound like this was true or false. And so it turns out it's true. But now we sort of have this gigantic gap between the upper bound and lower bound. So, so it's a problem where our intuition is pretty weak. And maybe one reason for that is that it's pretty hard to see how to work on the lower bound. Like I sort of feel like by now, this is already like 7 years old, and I think the techniques here were like, okay, we sort of see that the techniques we know are not going to sort of push the upper bound lower than this. So maybe one might hope that that's the right answer. There's clearly sort of a wall in terms of what we can prove in the way of the upper bound, but we don't really have any like good way of generating examples to make the lower bound higher. We're just sort of limited by our ability to come up with stuff. So, so with that in mind, let me say something about sort of how to bring computation into this problem. So, yeah.
How much the numbers matter, but the 2.208 to the fourth is almost 24. Seems to, maybe it's 2.108.
Oh, maybe.
Which is just under.
Okay. Yes, I did not actually write down this number, so it's some number that's a lot smaller than 3 in this, but is somewhat bigger than 2. Yeah, sorry. So the question that I talked about with a large group of researchers at Google DeepMind is, can machine learning be used to generate new large capsets? In other words, like capsets that are larger in various dimensions than any that have been devised. And there's many ways you could go about trying to do this. But they had a very interesting protocol that I now want to tell you about, because I thought this was kind of a crazy idea, and I was rather surprised that it worked as well as it did. So maybe I'll say, traditionally, if the word traditionally can be used for a field that's like in this form, kind of like 10 years old or whatever, but let's say, so traditionally, one might use a neural network to optimize some function. Maybe you would try to learn sort of some function f from z mod 3z to the n to r, so a real valued function, because like usually the machinery of neural networks, what they do is like learn real numbers because they involve, actually, I mean, how many of you guys, I'm curious, how many of you guys have ever like touched a neural network, like tried to train one to do something or something like that? Okay, so just the youth, I see. Okay, no, okay, so you know that typically what you're doing is the output is sort of some very complicated function from real numbers to real numbers, or from a real vector space to a real vector space, and it's doing doing derivatives. It's doing gradient descent. So there's sort of something fundamental. But I mean, if you want a solution to a combinatorial problem, you could say try to find a function such that if you say, so S is the, then you can threshold and say, okay, my set is the set of x such that, let's say, f of x is positive. And then you can try to optimize the function to make this set as big as possible while also not having any violations. And I mean, I think people have tried to do that and sort of like not gotten such great results. And even if you did get a result, what you would have, and I think those who have tried to train a neural network know this, and those who don't, I'm telling you now, you would get some like immensely complicated function, you know, which had like a million layers in it, and you would just look at it and be like, okay, well, I guess that works. I guess that gives me a large cap set, but I sort of don't know what to make of it. So let me tell you this kind of different mechanism that the folks at DeepMind wanted to try. Which is so idea instead of searching a space of real valued functions search a space of programs whose output is a subset of z mod 3z to the n. And this sounds cool, but makes no sense, right? Because what is the space of programs? Like that space of functions there is like literally a space, like a vector space. A space of programs is not really well defined, but that's okay. I'm going to show you how you can search it anyway, even though it's not well defined. So here's a mechanism. I'm going to draw on this board. I'm just going to draw sort of like a cartoon of how this process, which they call fun search, works. Okay, so you start with a million programs. Where do you get them? Maybe you like literally generate them randomly. And by program, I mean like a program, like in Python, like literally like a program, like you would like type in and run. And not, you know, they're not very long, right? We're talking about programs that are maybe like, you know, 50 lines long max. Okay, so you have a million programs. Then you run them. And maybe most of them don't run. That's okay. Still, some of them will run. And you do, as I say, they're not like literally random strings of text that you like put in a Python interpreter. Like you put in a skeleton so that if they output at all, the output is of the form some subset of vectors. And you run them all. You throw out all the ones that don't run. You also throw out all the ones that don't actually give you a cap set. And then you look at which ones give the biggest cap sets. So run them. Do they output a cap set? And then pick, let's say, the 100 best performers. And then you have a much smaller cloud of 100 programs. And the numbers 101 million are not principled in any way. I mean, they sort of tried lots of stuff, and I don't even remember. I think these are like roughly the right order of magnitude of the numbers, but like, I mean, you can just think of it, if you like, as like a large number and then much smaller number. Okay, now if this was all we did, it would not be very good. Right? I mean, you would probably not be likely, even among all of your million that you generated completely randomly, your best performer would probably still be pretty weak. And also you might notice that there's like no machine learning yet. Right? Because all I did was like run a lot of programs and then use this kind of assessment mechanism to just sort of count how big their output was. But then the other arrow is you have some large language model that's trained on like a large amount of code, and then you just sort of take these 100 and you say, give me 1 million more like these. And then you just cycle. Now this seems extremely stupid somehow, or extremely optimistic. Sometimes those two things go together. And I'm in drawing this cartoon, I'm papering over a lot of details that are actually kind of important. So I don't know how many of you folks are like sort of math CS double majors or think about this stuff, but really what's going on is this is kind of in the world of genetic algorithms. And so it's not quite like this. It's like they sort of have like a bunch of this is sort of taking place in parallel, and there's a bunch of different little islands where the programs live so that you sort of maintain, so they don't all sort of like collapse down into being one kind of program. You don't actually give the LLM 100 things all at one time. You kind of take them in pairs and kind of say, like, give me a new one that's like these two, and you do that for like sort of some large sample of pairs. I mean, so there's a lot of implementation details. I think to some extent these actually matter in terms of performance, but I mean, from a math point of view, I just want to sort of show you what kind of process this is, and say that it's surprisingly simple. And one thing I really want to emphasize is that the machine learning part, which is here, so maybe I should say sort of like LLM, comma, give me more like these. Somehow the machine learning part is not the optimization part. Like again, for those of you who've trained a neural network, what you would be doing to this function would be, because you have an objective, you have a feature you want this function to have, and you sort of make little changes to it, seeing like, does this change improve the objective you're looking for? And that's how you know which change to make. Here, all of the optimization, all of the improvement part is not done by the large language model. It's just doing by this sieving from 1 million down to 100. So it's done by this part that's like very fast, very objective, and like, you know, the part that like burns down the Ecuadorian rainforest is like up here. But it's not. But this is not the part that's optimizing. This is just doing similarity. This is just saying, here's 100 programs. I'm agnostic to how they were picked or what they're trying to do. I just want you to give me more programs that somehow remind me of those. So I find it quite remarkable, to be honest, that this works at all. I was game to try it. And so let me tell you how well it works and also what its limitations are at present, because I think both are pretty interesting from the point of view of like what we see as the prospects for generating progress in math. So and then we'll be just about done. Okay, so surprisingly, to me, this process matches best known cap sets for n 1 through 7, and improves f of 8 from which was previously known to be at least 496, and this method generates a program that gives one of size 512, which is the biggest known. That turns out not in itself not to improve the general lower bound, because but there is a way, which I'm not going to talk about, to sort of use it combined with Adol's approach to very slightly improve the lower bound I gave by like about 0.0001. But I will be honest and say that then, I mean, then Eric Naslund was like, come on, I can get like 0.0002, right? I mean, so I don't think, to me, the value is not so much sort of fighting over this exact number that's a little bit more than 2. And so the only problem with giving this talk on the board, and in general I like talking on the board, but the only problem is that then I don't have a slide that shows you what this code looks like. Because I have to tell you that from the point of view of the mathematician in this collaboration, the most interesting part of it psychologically is looking at this code that the LLM generates, like sort of through these many generations, and sort of, you know, trying to learn from it and figure out what it's doing. And I would say that the sensation is, one can't help anthropomorphizing a little bit and say like, to try to figure out what the code is trying to do. From my point of view as a mathematician, I mean, there's a philosophical question about whether that language even makes sense. But maybe I don't care so much, or maybe it's sort of not what's mathematically relevant. I mean, I think the question is, do we come out of it with new ideas about the problem? So I think, let me say, I think a lot of times the discourse around this is kind of like, are these machines sort of generating anything new and interesting and creative? And some people would say like, no, they're just sort of doing nothing and predicting tokens. And others would say like, oh yeah, they're doing everything and we should just like run large language models instead of thinking about math. And I want to emphasize that if I have one takeaway point from what I learned from this project, it's that I think there's like a vast intermediate ground between those two extremes, which is kind of where I think we are and very possibly where we're going to stay. So again, this is a positive result that we actually were able to like generate a pretty short chunk of Python code that generated like a new combinatorial example that was better than humans have been able to come up with. On the other hand, if you take this code, which starts with n equals 8, right, because it was trained on 8 dimensions, and then you're like, okay, let me now like change that first line to like n equals 10 or n equals 13 or something like that. Is the performance good? No, it is not. It is quite bad. So I mean, I think one question that we started with was like, is it possible that training on small dimensions, it'll produce some code which when you run it for any n gives like new big examples? And I can't say that's impossible, but I can tell you that that totally did not happen. So, so none of the code gives good results for general n. And actually, if you want to know, like, what are the mechanics of a collaboration between mathematicians and industry computer scientists look like? I mean, one of my roles would be, I mean, they can sort of say, oh, I ran it for n equals 13 and it was like total trash. But what I can do is like look at the code and just like actually on paper figure out what would this give for general n, right? Which they can't do by experiment, and you have to actually read the code and like work out what that program would give if ran with a general n. And actually in every case that I was able to work out, seems to get stuck at cap sets of size constant times 2 to the n. And sometimes that constant's bigger than 1, which is kind of cool. But it seems to sort of get stuck here. So maybe one way of saying it is that as humans, when we think about this problem, well, I sort of erased a relevant slide, but you know, we observed, and most human mathematicians who think about this problem sort of rather quickly observe this, this inequality, which comes from the fact that if you have 2 smaller solutions, you can put them together into a bigger solution. That's like a pretty fundamental part of our thinking about mathematical problems, especially in combinatorics. And in some sense, the machine seems not to get that. I think if you squint, there are places in the code where you can sort of feel like if you guys like grade papers when you're like, I really want to find a way to give like 2 points out of 5 on this answer. I think if I really think I can sort of see the rudiments of the idea for the correct solution, you can kind of do that with like some of the code. But I would say on some level, it's like not figuring that out. And I think that's kind of like why it gets stuck here. But what I think is that between can you, for a single dimension, train for a long time on that dimension and get an improved single example, versus can you just get general algorithms that work for all n, intermediate is can we generate code for a fixed n which gives the human reader a good idea for general n. And to me, I think this place is really the most interesting part of the way this subject is developing. And because there's nothing like science fictional about will this work. I think this is where we may already be like once we come into more contact with these problems. And so I'll just close by sort of saying like, for this particular problem, there were definitely moments when, as I sort of figured out how the code was working and how it was giving a good example for a particular n, it really did give me ideas for stuff to try and think about. Now, none of those ideas worked, but as you guys know, a lot of our ideas don't work, and I feel like already, if the program was doing something interesting enough to give me, somebody who's thought about this problem for many years, like being like, oh, I hadn't thought of trying to do it that way, like let me sort of spend a week trying this, that already to me is very promising. And I can say, see, if we had more time, I would tell you about a great project that my undergrad researchers did with me at Wisconsin that's kind of in a different problem that's relevant to that. Maybe I'll just close by saying, telling another story which also is an interesting story about the difference between kind of what we do in pure math academia and what's done in industry, and is also relevant for this question of how these collaborations are going to work, which is that we worked on another problem called Shannon capacity of graphs. I don't know, I know there's a bunch of graph theorists here, so I don't know if people know about it. It doesn't matter exactly what it is, but it's something that's notoriously hard to compute and that you can get bounds on by generating interesting examples, just like this. So this is kind of buried in like the supplementary material in the appendix to this paper, and I'll explain why, because they actually found a very short program that gave a very nice result for the Shannon capacity of the 7 cycle, the graph that's just a heptagon. And I thought it was interesting that it was so short, and I looked at it and I thought about it. And that particular program, I was like, oh, like I actually see what this is doing, and I see why actually this works and gives a lower bound for a general odd length cycle. And that was really cool. But then of course I was like, this is too good, this must be known. And indeed, once I knew what to look for, then I was able to find it in like somebody's paper in like Journal of Combinatorial Theory from like 1970 or whatever. So I just want to sort of say it's an interesting cultural difference that we have to be aware of when we're working in collaboration with industry, that for the folks at DeepMind, they were like, oh, well, too bad, like this does not give anything new, it doesn't beat state of the art, like, and so it's sort of relegated to sort of a small mention in the appendix of the paper. To me as a mathematician, I'm like, this is fantastic, because this was definitely an idea that like in the 1970s, like, you know, 25 years after the Shannon capacity is introduced. So if the machine is generating code that's good enough to give me an idea that's good enough to be in a paper, okay, this time it was something that was already in the literature from 1970, but there's no reason to expect that it has to be, right? So I mean, I feel like, I truly feel like there is a lot of promise for using these machines to generate I think especially this protocol of generating programs, of not just giving examples where you look at a sort of list of vectors and you're like, I have no idea what to make of it, but of giving a program that a human being can read and try to think about what it's trying to do and what ideas it might give us for further problems. Okay, so I'm a little bit over where I'm supposed to be, so I will stop there. Thank you guys so much. And let's get a picture taken.
Questions for Jordan?
Yeah. Oh yeah, and they might not even be correct because I sort of didn't write them down. Well, okay, mine is correct. The lower bound like really is literally from examples. It's like, so all the lower bounds are like, I come up with some example and maybe I tweak it in some way, and like, so 8L, and then that was improved by Tyrell like just shortly before our paper, and then by Naslund more recently, and it's an example of sort of basically working harder and harder to find bigger and bigger examples. The upper bound, it comes from this argument on what's called like slice rank of a tensor. So it's it's basically like, yeah, it's something that comes from like how far you like cut off like a binomial distribution in order to get a certain amount of weight in the tail or something like that. So that actually is some actual real number that has like a theoretical meaning that you could compute. Yeah.
So, like you said for general N, the model kind of failed, and it wasn't able to reduce it. But we have like you wrote that, you know, we have these restrictions. Why not like just give in the original font search like more restrictions like that you know require the model to be better, or is the simplicity in kind of just generating a lot kind of key?
So that's a great question. So one of my roles in the collaboration was to be like, let me suggest some built-in functions that seem like natural things to think about to like help the model do better. And it didn't, which I found a little disappointing. So somehow, like one of our ideas was like, let's actually inject some mathematical intuition about the problem into what we're encouraging the model to do. And somehow that didn't seem to improve performance very much, like a little bit disappointingly. But I will say that we didn't directly try to build in what's called the compositionality. And I think that's an active, I have a grad student, Karan Srivastava, who's working on this, but I think it's an active, I think it's a well-known problem that sort of these machine devices are not so good at like putting things together that they've already learned into new things. And I think that it is an active area to be like, how could we try to encourage it to do that? But no, we don't really know how. I would also say that probably, again, psychologically, I think, in ML world, they really like the idea of doing it from zero, right? So I mean, I think that they, like, in other words, they really liked learning Go just from the rules better than learning Go from like a lot of existing human games. So I do think like in the world of ML people, they kind of like the idea of like, let's not inject, let's see how much we can do purely from the rules of the game, so to speak, without injecting too many of our pre-existing biases about how to approach the problem. But in this case, I do think our biases would be helpful here, because I think there's some useful bias that we have towards like putting smaller solutions together that so far it's not picking up by itself. Yeah?
So one consideration is like how like limiting the number of like how big the code you generate is. And I'm assuming that has to do with wanting it to be explained a little. Is there any like work done already about kind of what's the relationship between how much code we need to generate? Like is it possible that we needed more code to generate and would get much better results? Or is there anything like, is there any work being done on that and like how to find that balance? Or?
So I don't think they put a hard upper limit, and I don't know how much they weight shortness of code. And it is like, it's important to point out that, right, there are these sort of formal notions of complexity of a program, and somehow, in some sense, what it's okay, let me give you an example. A very short program would be the program you could write that like literally exhaustively searches all the vectors and gives the biggest one. And that would have the advantage of provably giving the optimal answer. So one part of this process that I didn't write down is some of these guys will compile and you start running them and they just don't finish, and then you throw those out too. So it is kind of punishing code that might be short but has like essentially infinite runtime, right? Those will not survive. So in some sense, I think what it's privileging is more like things that run fast, not things that are short. But as you can imagine, often shorter things run faster, so.
Yeah, okay.
Yeah, Mike. Could you say a quick word about the process from going from right to left? Is it sort of like, give me 10 to the 6th? Like, yeah, I'm used to thinking of like an LLM as predicting like what should come next, like what program should.
Right, but sort of given some prompt, it can produce like sort of some long chunk of text following it. So like literally, what you would have is you would have these sort of 100 surviving programs. You would take a pair of them, and then your prompt would be like, here's 2 programs. Like, give me a program that's like these, right? And then it goes like chunked to the same way you could sort of give it 2 paragraphs and say, give me another paragraph that's like these, and then you run that 1,000,000 times. So it's, so yeah, I mean, it is, I think the functional way it works is like next token prediction, but you just like do that until one of the tokens is like, the end of a program.
But what is that next token prediction trained on? Is it?
Oh, so I should say, they have an LLM that's trained on lots and lots and lots of code.
Okay.
So that already exists. So it's, that's something that they had already. So there was no training of an LLM as part of this project. They used something they already had, which is called Pokey. But what they said is that they did try, there's a lot of LLMs trained on code, and they said they didn't seem to matter very much which one they used. So I should say that, my hope for this whole kind of project is that it's not clear you need as much compute as DeepMind has in order to do it. And so like my hope is that we'll sort of be able to like build out versions of this that we can just do, like without having to go through DeepMind for each question. So we'll see. Yeah?
Some folks have tried doing this without the LLM part, sort of like just using genetic functions or like genetic algorithms to construct, I guess, examples that maybe are
Yeah, so I think that is a great question, and I don't know if people have done it. So yeah, I should emphasize that, like, again, it's very natural for like a company that has a cool product to be like, what can we do with like the new thing? And I absolutely do not know how it would compare if you tried doing this with sort of with older methods here, but sort of like using, if you gave it like the same amount of compute as those guys have, which is a lot, and sort of built a more old-fashioned genetic algorithm type thing to sort of try to improve your function. I don't honestly know what would happen. So I absolutely cannot, I'll say this. The traditional genetic algorithm would sort of give you some output that was like, it would be easier to do it on like functions, which might be less readable. I mean, I do like that this sort of very naturally produces like Python code that you can just like look at with your eye, and it looks like human written code, and you can sort of, it somehow does feel more interpretable this way. But in terms of the performance, I actually have no strong reason to think this is definitely better. Yeah?
So I know with like chess or Go, when a lot of the top players talk about, oh, the engines, what they're doing, like the moves that they're playing seem completely crazy to the human understanding of the game. You were talking about how these LLM generated codes are giving new ideas. Are the ideas like roughly comparable to a lot of the known techniques, or are they just completely out of left field, unrelated to what happened with the product?
Yeah, I would say they're different. As I said, they don't do things that we would naturally do, like putting together smaller solutions. I can't resist saying, and then we should probably stop and go take our picture, right? Like, in fact, to make it work, they found that they needed to restrict to an incredibly restrictive class of programs, which I also thought was not going to work. But you're going to laugh when I tell you this. But in fact, the program skeleton requires them, the programs work like this. They actually assign each vector in the space a score, and then you just add the vectors in order of their score. But if one creates a line, you skip it and move on to the next one. That is very bizarre. That's like if you wrote a chess engine and you were like, before the game starts, I'm going to rank all possible moves by how much I like them. And then at each stage, I'll play like the highest scoring move, which is legal in this position. But the scores were determined in advance, like with no reference to the board. I mean, that's weird. So it's sort of weird that it works as well as it does. And that's definitely not the way that a human would think about the problem. But I mean, I think sometimes what happens is you can read something written in that way and be like, oh, I see how this is sort of doing something that feels natural and is related to the way that we think about it. So I wouldn't actually say that it feels alien in the way that sort of some chess players have described some of the moves that come out of the engines. All right, maybe we should have, we're supposed to get our picture at 10:45.
We're going to get our picture. Let's
okay, but I'll be there at the picture so people can ask me more. So thank you guys so much.